Imagine that we were to shoot out a singular bullet at a snowman on Mataro using our H82 rifle on Roblox. Some people have been speculating the fact that because it's a video game, we don't really care about physics, and that the laser being shot out would actually mathematically be enough to destroy the entire Earth. Now, it's a very fun thing to question, a very fun thing to fancy, but let's do the mathematics to determine if the bullet is actually enough from one singular shot at a random snowman on Ontario is enough to destroy the entire world if we were to apply real-world physics into what we see on the screen. So in this analysis, we modeled the laser trajectory as a piecewise parametric space curve embedded in three-dimensional Euclidean space using the equation r of t is equal to the vector of x of t, oops, that's a horrible t, y of t, and z of t. So, pretty much this curve right here, this red laser line, this will represent as L. So for later context, if I mention L, I am talking about the laser. L for laser. So, if we were to go ahead, we have another equation. The total displacement along the curve is defined by the arc length functional. So, L equals the integral from a to b of the magnitude of r prime with respect to t. So this is our equation. So while that seems difficult at first, it's very easy to implement just by taking L equals 10.5 plus 35 plus 24.5 plus 35 plus 22.75 plus 57.5, which of course is drawn from the dimensions around the map right here. So, in other words, L equals 185.25 studs. So now that we're trying to figure out the speed of the blast itself, this came in the matter of one frame on my screen. I have a 144 hertz monitor, so at the refresh rate of 144 hertz, a single frame corresponds to the reciprocal of the frequency. So delta t equals 1 over 144 seconds. So this is the amount of time that the bullet took to travel. So branching off this, we can take the velocity formula, which of course is just v equals L over delta t, and then plug in everything in. This just simply becomes 185.25 divided by 1 over 144. And if we calculate that real quick, let me do this in my head. V equals 26,676. And of course, the V is the velocity magnitude. So now, if we want to use the small arrow tangent of it, we need to go ahead and take this equation right here, which is that V of t equals the derivative of r with respects to t. So, and then it would take the change of direction, a of t equals the second derivative of r with respects to t. So you can write it like this, or alternatively, of course, you can just do something like d that, but that's besides the point. So we want to go ahead and calculate the curvature with that data. We need to go ahead and run the equation that kappa, not k, equals the magnitude of r prime of respect to t times r double prime of t over the magnitude of r prime of t to the power of 3. This describes the instantaneous rate at which the direction of the trajectory changes. So if we had a higher budget, we would go ahead and put a polar grid centered on the shooter, something like this along the lines, but just more detailed. But considering this is in paint.net, we gotta use our imaginations, but we can still apply the math. So essentially the theta of the arc, of course from the shoot based on the location of the shooter, we can use x equals r cosine of theta, and then y equals r sine theta. So this expresses the displacement in terms of radical magnitude and angular rotation, which we take our next equation, which is the calligraphic L, which is not an L, it's a different model, it's a Greek letter, equals kinetic energy minus potential energy. So T, which is kinetic, equals 1/2 of m times the magnitude of v squared, which becomes T equals 1/2 of 26,667 squared. 67, you got that. Or, of course, we can write it simply as T is approximately 3.56 times 10 to the power of 8. So that is our kinetic energy. And then we go ahead, we got to give an even bigger equation right here, which is derivative with respect to t times this is derivative of time to the partial derivative of L with respects to q dot, not k dot, q dot right here, minus the partial derivative of L. This is a beautiful partial derivative of L with respects to q equals 0. So using this, we know that V is approximately 7,470 meters per second. And if you're wondering where I got meters from, this is based off mathematics determining the size of a stud compared to a meter. So that's just based off our earlier rate. And we pretty much got to apply the equation of gamma equals 1 over square root of 1 minus v squared over c squared. So this is the Lorentz factor, and this approaches unity under these conditions. So our final distance is 185.25 studs based off its location, and the speed of it is 26,676 studs per second. And the laser traverses 185.25 studs in one frame, corresponding to 26,676 studs per second, governed by parametric kinematics, curvature theory, Lagrangian mechanics, and relativistic transformation. So it may seem like we are done, but we got to also go ahead and take the magnitude of the force of this singular shot from our standard H-82 assault rifle. So first off, let us officiate the mass of the projectile to 0.05 kilograms, just to be fair. And the projectile, we need to know the momentum of it, which is P equals mv, also which is momentum, because momentum equals mass times velocity. So P equals 0.05 times 7,470 studs a second. So the momentum equals 373.5 kilograms per second. So now we need to get force via the impulse. So force is the rate of change of momentum. So that is F over delta P divided by delta T, which of course is the change in momentum and the change in time. So we're going to assume the impact duration of the bullet is about delta T 0.001 seconds, as this is pretty much the time it takes for the weapon to, for the bullet to pretty much register that it hit the snowman. So the duration is about 1 millisecond. So the force exerted on the snowman is 373.5 divided by 0.001, or the force is 373,500 newtons force being applied. So if we want to go ahead and apply Newton's third law, well, the force of the Earth is about 373,500, as the snowman exerts an equal and opposite force here on Earth, as it seems unchanged. So we need to get the acceleration of the Earth, which the mass is pretty simple. The mass of Earth is 5.97 times 10 to the power 24 kilograms. If you were wondering, I did have to look that up right before I did this part. So Newton's second law makes it clear that A equals F over M. A equals 373,500 divided by the mass of the Earth. So I'll just write these quotation marks so it notes that. So A, or acceleration, imparted to Earth is approximately 6.25 times 10 to the negative 20th meters per second squared. Now, that's not all we got to go for. We also need to take a note for the rotational impact on the Earth. So the torque of the Earth's center is about gamma of RF. So let R equals 6.37 times 10 to the power of 6. So gamma equals about 6.37 times 10 to the power of 6 times 373,500. Also theta equals 2.38 times 10 to the 11 newtons. All right. Now we need to get the moment inertia of Earth as well. So inertia equals 2 over 5 r squared, or inertia is approximately 9.72 times 10 to the power of 37. And we want to get the angular acceleration. Well, it's pretty simple as well. That is just in the theta over I. So we plug in what we got earlier for both these things previously. The angular acceleration is about 2.45 times 10 to the negative 27 radians per second squared. Now, when you get the gravitational field perturbation as well, as we would need to get the gravitational force of the Earth itself based on the impact that our weapon of mass destruction has. So from Einstein's field approximation, we take G of UV equals 8 pi G over C to the power of 4 UV. So this translates to pretty much a localized energy injection slightly perturbed space-time curvature. However, the fractational change in Earth's gravitational binding energy, which of course is is approximately 2.24 times 10 to the power 32nd joules. The laser kinetic energy, which is E equals 1 over 2 mv squared. So we plug everything in. That'll become approximately 1.39 times 10 to the power of 6 joules. And if we get the fractional perturbation, E over U is approximately 6.27. I'm sorry, not 6.27. 6.2 times 10 to the power of negative 27. So the impact delivers 373,000 newtons of force to the snowman, imparts an acceleration of 6 times 10 to the negative 20th meters per second squared to Earth, induces an angular acceleration of 2 times 10 to the negative 22nd radians per second squared, and perturbs space-time curvature on the order of 10 to the negative 27th. Now, I know these numbers sound pretty big, so you're like, wow, this Roblox game is very unrealistic. These laser guns must just destroy everything in sight, and realistically it would destroy the Earth. Well, you're in luck. If this happened in the real world, the snowman would experience a violent localized impact, but the Earth would experience a momentum change so small it's effectively indistinguishable from zero, and the structural integrity of the planet will remain entirely unchanged. Space-time curvature will remain unaffected in any measurable way. The Earth would not explode. It wouldn't even crack, not even respond. The Earth wouldn't even notice. If you're curious, I did some further calculations, So the impact contributes about 6 times 10 to the negative 27th of the energy required to unbind Earth, and that is 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 of what would be required to pretty much cause the destruction of the Earth. So our hypothesis of a laser gun being shot on a Mataro is being enough to destroy the entire Earth based on just mathematics is completely false, and anyone who claims otherwise is an idiot. Thank you.